Our next root finding technique that we're going to study here is called false position. And you can see we pretty much have the same picture here that we had yesterday. We have some function here in red, f of x. And then maybe we spotted this graphically, maybe we used our incremental search function, but we have bracketed this root between x lower and x upper in the exact same way as when we were talking about the bisect function. And in fact, this technique that we're going to use, we're only going to have to manipulate one line of code from our bisect function to switch it to this false position. But most of the time, this false position technique is going to converge quicker on the root. Okay, not every time, but most of the time. Okay, well, let's see how it works. So is what we'll do is from our x lower, we'll go up to the graph, and same with our x upper. Okay. So I'm looking at those y values there. And had I sketched this perfectly, or with a little bit more curvature, we probably wouldn't have the issue that we're about to have here. But so what we'd like to do is connect those two with a secant line. There we go. All right, and you can see that we're actually really close to the root here. A little closer than I'd like because it's going to be hard to label what we have going on here. But where this line intersects the x-axis, that's going to be our x sub r. Right? This was our estimate of the root yesterday. We used x sub r for that. But previously, what we had done is we had just divided or averaged our x lower and x upper. We went directly in between the two. Now, next, the question is, well, how do you actually come up with xr? We see it geometrically. We need to know how to find this algebraically so we can, so that we can code this. Okay. Well, let's first try and come up with the equation of this green line here. So I want you to first note that one of the points on that green line is xl, comma, f of xl. And the other point, this one here, is going to be x upper, comma, f of x upper. And then if we're trying to find the equation of this line, we can just use point slope form. So how about we use this point right here? So we'll have y minus the y value. So that's f of x upper. And then we need the slope. So if we're trying to find the slope between 2 points, that will be f of xl minus f of x upper all over x sub l minus x sub u, right? This is just the change of y over the change in x. And then the next thing that we'll do is we'll write times x minus, and so we did a y minus the y value of this point, so now we're going to do x minus the x value of that point. Okay. And this is where, well, we still have a little bit of work to do, but you'll notice that if you're looking at our textbook, it just automatically gives you the final formula you need without any derivation, and so we're going to derive that formula here. Okay. So the next thing is we have the equation of the line now. This is it right here. Okay. But how do we find x sub r there? Okay. Well, x sub r is the root, meaning that you would replace this y right here with a 0, right? I'm going to go ahead and do that. If I replace that with a 0, okay, well, that's equivalent to just not putting anything there. Okay. So here's our equation now if we let y equal 0, and our goal is to solve for x. That would be finding the root. Okay. So what we'll do is we will go ahead and let's multiply by the reciprocal of this fraction that we're looking at here. So we're going to have minus f of x sub u times x sub L minus x sub u all over f of x sub L minus, there we go, f of x sub u. And then we still have this x minus x sub u here. All right, and so this means all we have left to do is add x sub u to each side and we are done. Okay? And so I'm going to do that. I'm going to add this x sub u to this side. Okay? And then we have this minus sign here, so minus. And why don't we bring the f of x sub u just in the numerator of this fraction so it's a little more compact looking. So we'll have f of x sub u times x sub L minus x sub u all over. And then we have f of x sub L minus f of x sub u. And this is equal to x. We have found that root, x sub r. Okay. The only thing is we could just put a little r here to denote that that's the x value for that root of the green line there. Okay. And it ends up that is what we'll wind up doing is we will actually choose what to do with our interval x sub L and x sub u here in the same way that we did for the bisect function. Okay. And that is what I mean here is if we were to, let me actually maybe write this in here, we would take f of x sub L and multiply it by f of x sub r. And remember, if this is positive, that means that there is no sign change. And if it's negative, it means that there was a sign change. And so you could see f of x sub L in this picture is negative. But if we were to plug x sub r into f of x, that would give us a positive. So we would have a change in sign here, right? Which means that in between x sub L and x sub r, there's a sign change, right? Which also means that there is a root in between there. So is what we would want to do is our next interval, if we were to keep going with this, our next one would go from here to here. So our x sub r would become the new x upper. But I probably didn't need to cover this part in as much detail because, again, this part of our code isn't going to change at all. It's just that our formula for x sub r is now going to be a little bit more complicated. It's going to be this thing right here. Okay? And this matches exactly what you see in your textbook. All right, so what we'll do is we'll switch over to MATLAB and we'll make this quick edit. We are in MATLAB now, as you can see, and this I've already saved this file as false position because that's what I'm going to name the function. But let's just go over to our bisect function. Let's first just copy and paste this top line because we're going to have all the same features on the function. All right, and let's paste. And now let's just change the name of the function. We probably don't want it to still be called bisect. How about false position? Okay. And then I'm not even going to bother with the comments here because they're the same. Let's just copy the code now from bisect. Let's see. Ooh, went a little too far. There we go. That looks good. And then we're going to go up and change that one line that tells us how to find x sub r, this one right here. We're going to make it a little bit more complicated. So we're going to have, what was it, x sub u minus And then we will have a fraction here, right? So then we'll have f of x sub u times, and then we should have x sub l minus x sub u. And then, so that's our numerator, right? And then we want to move down to our denominator. And the denominator should be f of x sub l minus f of x sub u. Okay. And let's see. That all looks good. Other than one thing. There is one issue here. If we scroll up, it's func, not f. So I need to come down here and change all those f's to funcs. Yeah, right here. So func, and func. There we go. And now let's just go ahead and save this, and we'll go back to our bungee example. We'll test this out, and I also want us to compare how quickly this converges. Okay, so let's see here. Let's do, just to make this easy, let's go ahead and copy the top line of each one of these. Other than the word function. All right, and since we're going to be using f for our function on each one of these, let's change those to f. Okay. And then let's use the same x lower and x upper for each one of these. How about we do 120 to 160, and we'll do that here as well, 120 to 160. And let's just use the defaults. So let's just get rid of the rest of this. And the thing that's going to be nice here is when this does display, we're going to get the number of iterations, the relative error, the function value, and the root. And so we'll be able to compare these two algorithms here. Okay. All right. So you can see that this bottom one here is our false position. It took 7 iterations. And is what we're going to see when we scroll up is that bisect actually took more iterations. Okay. So let's see. Maybe I should just move this up like this. Okay. So yeah, here 19 iterations for the bisect function. So this reached the relative error much quicker using false position. Okay. Now, I did mention that while oftentimes false position is quicker, there are cases where it's not, and there's a great example in the book that I'd like y'all to look at where this does not occur. So having multiple tools or techniques can be helpful depending on which problem we're trying to solve. Okay. But that's it for false position.